In this lesson we are finishing up our little bits of characteristics of stars. And we're starting with star distances, or distances in space. Okay, because space is so vast, distances in space are measured in light years. We're not using kilometers or miles because our numbers would get too big. A light year is the distance light travels in 1 year. Okay, so a light year is a distance. Let me just underline that. A light year is a distance. The distance light travels in 1 year. The speed of light is 300,000 kilometers per second. So if you multiply it out, light travels about 9.5 trillion kilometers in 1 year. That's a light year. Light from our sun takes 8 minutes to reach Earth, so we can say that our sun is 8 light minutes from Earth. So if our sun blew up today, you would know about it 8 minutes from when it blew up. Okay? It takes the light 8 minutes to get there. The closest star besides the sun to the Earth is Proxima Centauri. So the closest star is the sun. Second closest star is Proxima Centauri. It's 4.3 light years away. Sirius, which is the brightest star in the sky, besides the sun, is 9 light years away. So again, you think about it, and okay, if Sirius suddenly blew up, we wouldn't know about it for 9 years. Okay? So if we go outside and we see it exploded, we know it happened 9 years ago. Polaris is 700 light years away. Okay, so imagine how bright it must be that we can still see it, and it's 700 light years away. Betelgeuse that we've talked about, Betelgeuse is 643 light years away. It's the 9th brightest star, and it's still 643 light years away. So again, just think about how bright it actually is. Rigel, we talked about that in Orion. It's the 7th brightest star. It's 770 light years away. So these are incredible distances away. How do we figure out how far these are? We haven't gotten in a spaceship and traveled to any of these stars. Okay, we haven't seen that Betelgeuse is 643 light years away. So how do we know? Scientists use a method called parallax. And it's a way to estimate how far a star is by how it appears to move when you look at it from two different places in the Earth's orbit. And we're going to be doing a lab on it in a week, probably. Let's look at maybe this picture is a little bit better idea to understand parallax. So this is the star that we want to figure out how far away it is. What we do is we look at it at one time in January. So here's the Earth in January, and we look at this star. And we compare it to these background stars. So here are the background stars. And we see that, oh, the star is right in the middle of these 4 stars. Then we look at that star again in July. And now we see those same 4 stars, but now A has moved this distance. Okay. By using parallax, we can figure out how far the star is away based on how far it appeared to move from July to January. Okay. Like I said, we're going to do it in class, so you'll get an understanding of how it actually works. It might seem confusing here, but just think of it as we look at a star at 2 different times during the year. The star will appear to move when you compare it to the background stars. By how much it appears to move, we can tell how far away it is. Star magnitudes. We're getting kind of 2 topics left, and these are the 2 most important characteristic topics. First one is star magnitude. Magnitude is a fancy word for brightness. Okay, so magnitude means brightness. And there are going to be 2 types of brightness. It can be apparently bright, or it can be absolutely bright. And we're going to start with apparent magnitude. So the visibility of the star depends on how bright the star is and how far away from Earth it is. How bright a star appears to be, as looked at from the Earth, is called apparent magnitude. We can see over 1 trillion stars with telescopes, but only about 6,000 with the naked eye. This might be confusing, you just have to remember it. Bright stars have low numbers, like a 2. Dim stars have high numbers, like 18. So if you had a star that was -3, a very low number, it's going to be a really bright star. But if you have a star that's something like a 7, That's a pretty dim star. It's a fairly high number. We couldn't see a 7. We can see kind of 6s and under with the naked eye. Okay, so kind of negative numbers up to 6 we can see with the naked eye. 7s and up we can't see. They're too dim. The Sun is obviously the brightest star. Its apparent magnitude is negative 26.8. The faintest star observed with the telescope is about a plus 29. I've seen some other things that with our new fancy equipment, we've seen things as dim as plus 36. So kind of think of our range as going from negative 26.8 as the brightest to about a plus 36 is the faintest thing that we can see. Absolute magnitude is the true brightness. Apparent magnitude was how bright they appeared to be. Absolute magnitude is the true brightness. And how we figure that out might seem kind of weird. There is a good rationale behind it. I'm not going to explain it here, though. What we do is we say, okay, what if all the stars were the same distance from Earth? Then let's compare how bright they are. And the distance they picked was 32.6 light years away. So just think about moving whatever star it is to 32.6 light years away, and then we can tell its absolute brightness. So again, let's start with our star, our Sun. It has an apparent magnitude of negative 26.8, but its absolute is plus 5. We could barely see it. Moving it to 32.6 light years away would make it dimmer. So if we think of the Earth as here, I'm just going to put here is the Earth. Right now the Sun is really close. But if we moved it to this kind of imaginary 32.6 light years away level, the Sun would be moved a lot farther away, so it would be dimmer. It'd go from negative 26.8 to plus 5. Think about some of the other stars that we've talked about. We talked about Betelgeuse. Okay? Betelgeuse is, what I say, it was the 9th brightest star, but it's 643 light years away. So Betelgeuse is way over here, 643 light years away. So again, you think about it. Betelgeuse is in its last stage of life. Its next thing it's going to do is supernova, so this huge explosion. If it exploded today, we wouldn't know about it for another 643 years, because that sunlight would take 643 years to get to the Earth. Get so far away. But if we moved it up to this 32.6 light year line, it's going to be a lot brighter. It goes from being a 0.7, apparently, to a negative 5.5. It'd be incredibly bright. Sirius, which was a close one here, we talked about it, that would go from negative 1.5 and become a 1.4, so Sirius would get dimmer. The North Star, remember the North Star, Polaris, is way, way, way far away. It's a plus 2 right now, but if we moved it to 32.6 light years away, it'd be getting closer, and it would be a negative 3.6. It would be really bright. Okay? So apparent magnitude is how bright they appear to be. Absolute magnitude is how bright they actually are. Last topic. This is an important one. It's how we classify stars, and we're going to spend the rest of this lesson doing it. We classify stars by comparing their temperature with their absolute magnitude, their absolute brightness. When you do this, you get a pattern. And you can see this pattern by looking at an HR diagram. Okay, so this is a Hertzsprung-Russell diagram. The middle of the chart, so let me circle it here. This is the middle of the chart. This is called the main sequence. Okay, that's the main sequence. Main sequence stars are basically the ones that make sense. Main sequence stars, stars whose brightness increases as temperature increases. It makes sense. The hotter a star is, the brighter it is. Of course. About 90% of all the stars fit into the main sequence. So we look it up kind of close up here. We look at our axes first. On the right, we see absolute magnitude, so absolute brightness. Is it brighter going up or brighter going down? You see the negative numbers, so it's brighter up, okay, dimmer down. On the top is the temperature. It's in Kelvin, doesn't matter. Bigger number is hotter. So it's hotter to the left, cooler to the right. So again, we see the main sequence stars in here, and we see, kind of going this way, the hotter they are, the brighter they are. It makes sense. The hotter, the brighter. The sun is right here. It's not very hot. Oops, that was a bad line. Not very hot. Not very bright. It's yellow. We have some stars, though, that don't fit into the main sequence, about 10% of them. So we can just look at them. Down here, let's look at these first. These stars are really hot, but they are not bright. Okay? So they are hot, but not bright. That doesn't make sense. How can they be hot but not bright? Because they are small. Okay? Those are called white dwarfs. They're white hot, but they're really small. These stars up here are also exceptions. They are not hot, but bright. Well, how can they be bright even if they're not hot? They are huge. Okay? We're going to call these supergiants. Okay. We see this picture again. It's kind of a neat, fancy version. Main sequence, hotter the brighter. We see some of these things like Betelgeuse. It's not hot, but it's really bright because it's so big. The white dwarfs down here are hot, but not bright because they're so small. And that was kind of the last thing I showed here. We see Betelgeuse, huge and cool. They appear bright just because they're so big. And then white dwarfs are hot but dim. And why are they dim if they're hot? Because they're so small. That's it.